Empezamos entonces. Okay, hello everybody. So I have the pleasure to introduce you Miguel Heredia, who is a researcher from the University of Siegen in Germany. And today he will give us a talk about compressive sensing for the photonic mixing device. Okay.
Thank you.
You can start when you want.
Thank you, Paula. So effectively, today we are going to have a look at what we have been doing in the last, let's say, 4 years already, going around with the photonic mixer device and trying to apply compressive sensing theory to this technology. So this project was supervised mostly by Professor Ottmar Lofeld, which is a well-known person in the world of radar. He works in synthetic aperture radar, and also he is very active in compressive sensing theory. And also by Professor Andreas Kolb, which is also well-known in computer vision and has been working with time-of-flight imaging technology, 3D sensing, and is very, he really knows about the photonic mixer device. And we have been working, as I said, already like 4 years in this topic, and we will see mostly results. So the techniques we have developed and some visual results of what we have obtained. First of all, I would like to start with a very brief introduction of the ZESS, of our institute. And later I will go straight away with the introduction, motivation, and main goals of this work specifically, and the state of the art and our main contributions. And later the fundamentals we will look at will be mostly in two different dimensions. So first of all, what is this photonic mixer device? How does it work? And later, what is compressive sensing theory? So everybody hears continuously compressive sensing, and that compressive sensing is somehow superior to conventional sampling schemes, but sometimes we don't really know what compressive sensing means. And later, well, this is already getting into, into the work, into the dark part of the work, so more or less solving some preliminary issues that preclude the direct application of compressive sensing theory. So, some fixed pattern noise, raw data corruption due to SBI activation. So this is a mechanism within the pixel. We will see how it works and what is the problem exactly later on. And the operation in low energy conditions. So for example, we want to operate in an almost passive way, or we want to operate with really low exposure times. In such cases, we will have this problem here. Well, and finally, so the core of this work is actually, compressive sensing for the photonic mixer device. So this is the core of the work. We will see which are the domains in which we can actually apply compressive sensing, and within these domains, we will see we need a sparsity model, so we need to characterize the PMD pixels, modeling the transition from a high resolution domain to the low resolution domain where the signals live. And later we will see that we can actually try sparse recovery both in the spatial domain where the images live and in the time frequency domain where the modulation signals live. Right now, we have no idea about anything. This looks a little bit strange, but we will see it's very easy. You will recognize each of the domains, and you will see that it is actually natural to proceed in the way we proceeded. So, and we will wrap up with conclusions that will be probably exactly repeating what we did now. So first of all, the sweet part of the presentation. What is the ZESS, or who we are? Well, the ZESS stands for the Center for Sensor Systems. We are placed in the beautiful city of Siegen, which is actually very nice right now because it's summer. Everything is blooming, maybe too much, and we have sun from the very beginning of the day until the sunset. And my office will be probably around here. And this is a very early picture. Of course, the color is getting clearer and clearer. They are not yellow anymore, but we have a location that is very green there in Siegen. I think Paula knows. And now we will see more or less our organization. So first of all, we have different individual project sectors, so different projects that in principle may look individual, but we have a kind of horizontal connection, we have cooperations in between, and so on. And, and later, well, all these projects somehow span 3 fields of competence, mostly sensor development. This is the area where you don't really want to be because things do not work properly. No, this is just a joke, but definitely sensor development is being within the hardware, so to say, and things become complicated. And on the other hand, we have the area of application development. This is the border with industry, and this is the area where you will probably also do not want to be. And this is our area. Now, this is the central area of signal and information processing, which is somehow a natural interface between the core sensor development and the application area. And all our projects, more or less, could be classified or could be placed within these 3 fields of competence. And over everything is, of course, our executive board and the management office. And over this, we have our board of directors. And floating around, or better said, well, over them, of course, we have our scientific council and our industrial council that are external institutions that control the whole process and tell us, well, to which direction we should steer or which are the weaknesses, or, well, somehow they help us to improve externally. And later, of course, we are part of the University of Siegen, we have departments, and we have a close cooperation with the Fraunhofer Gesellschaft. So I think everybody knows the Fraunhofer Institute is a very well-known research institute in Germany. So what we do, well, we do high-frequency imaging, we do mobile robotics. How many people here are implied in robotics? 1 person. Well, I don't think so. Probably more people are somehow implied in robotics, but they still don't know. So this is a mobile robot, and here on top we see one of our time-of-flight cameras. You can recognize it probably because it has an array of LEDs. These are infrared LEDs there. And the good part of this is that you can substitute a relatively expensive laser scanner. So imagine these very initial SIG laser scanners that we used to mount in these mobile platforms. This really had a large cost, and of course is sequential. So one of these time-of-flight cameras could acquire the whole complete depth profile in a single acquisition. So of course we can use it for SLAM or simply navigation in a known environment, for defining safe areas in industry and things like that. Later we also have the area of Earth observation or remote sensing, for example using satellites, drones or planes, etc. Structure monitoring or structural health monitoring, distributed sensor systems and so on. Also, well, in a different area, the area of graphics, so simulation, computer graphics in general. We also covered that partially in cooperation with the GRK. Yep. And of course, a synthetic aperture radar, SAR image processing. SAR is, well, everybody knows that radar images and SAR images are often very noisy, so the processing to get a very clean resolved image where you can actually recognize or segment structure on the ground is very important, and is well, one of the focuses of the institute also. And one of our pearls, the ZESS multicam, is a 2D 3D sensor, so everybody knows probably the Kinect sensor from Microsoft, and many sensors that are multimodal. So you have on the one hand this RGB camera that is a conventional 2D camera, and on the other hand next to it a 3D camera or well, a time-of-flight camera in the 2nd generation. And in this case we have both cameras in a single system with a single optical path. So there is only one lens here. This is not a lens, this is the illumination system. Lens is within it, And then here we have a kind of beam splitter. It's not really a beam splitter. It splits by wavelengths, so you don't lose like half of the radiation for each side. And we can mount inside both the RGB sensor and the time of flight sensor without problems of registration of different occlusions and so on that we really get in the Kinect sensor or in commercial sensors. Well, so this is enough for a relatively close already overview of the center of what we do. And now we have to wait until the slide goes to the next. Probably it will happen, but it's good that it got blocked sadly in this one, because we are going to talk about time of flight. So definitely, oh yes, and now it's perfectly placed in the center of the image. Great. Okay. So what we can do, what we can bring in, what are the points where cooperations could be established. So first of all, of course, we work in developments of optoelectronics, sensors, and well, photonic sensors and things like that. But we also do the next part of the processing, so 2D, 3D image processing. Later, optimal sensor signal processing, and of course, when you talked about optimality in sensing, you have to talk about compressive sensing. Those are two of our main strengths. And remote sensing, as I said, SAR, high frequency imaging, and so on. Coherent diffraction imaging, we also work on that. Sensor communications and networks of sensors, so multi-sensor systems, it's also one of our active research areas. And of course, multimodal sensor system, multimodal imaging systems are a very important, relatively new area. So how to fuse information coming from different kind of sensors that are fundamentally different in the physics, but that later on what you get at the end of the day is information of a single scene. So the scene is one, the truth is only one. What you get are different views of the same truth. So how to process this information to extract what you want to know about the scene is critical, and you can work in a synergistic manner that you could not work if you had those sensors separately, independently. That's something to take into account. So how we do research? Well, we have, of course, as always, we have industry, technology, market, and of course, for this to survive, you need research and development. Yes, you need it. And for research and development, of course, we need a block here, which is the doctoral training. So you need to prepare the people that will rule this in the future. And this is where we come into the game, right? So we have several structured doctoral programs. First one, the IPP Multisensorics, which started in 2002. Later on, we have the research school Moses, which started in 2008, and we are part of the DFG research training group Imagine New Modalities, which started in 2009 and which funded this work. Well, this already gets in touch closely to, for example, the ETN that we were trying to prepare some months ago. So this is more or less the same structure we used for the Moses program. So we have the early stage researchers that stay at the center of our structure. We have, of course, associated partners and later, well, of course, ourselves as a center, several Fraunhofer institutes in that case. And for this to work, we need an interface here between the supervisory board and the early stage researchers, so the doctoral students. We have, well, recruitment and personal affairs, self-administration of the ESRs, and of course, the doctoral training, examination, and dissemination committees. So those are instruments that somehow control this whole block here, which is a lot of people, and that serve as interfaces with the supervisory board. And later, of course, this small block here seems to have a lot of importance in practice, the financial managing and reporting. So as an overview of the structure, And now we are done with the boring things, and let's have a look at real results. So let's have a look at how what we do looks like when it works. Here we have something that is called a bistatic SAR with a stationary receiver. So what we did mostly was to use the TerraSAR X, which is a satellite that is orbiting around the Earth, as an external illuminator of our scene. And later, we placed next to the scene this system which had a receiver pointing at the emitter, and another receiver getting the echo from the scene. And of course, both of them are mixed with thanks to a local oscillator, and later digitized. And this is our scene. So this is where the second antenna, well, both antennas were placed, these horn antennas we saw before. And this is the valley that is in front of the university. This is the area of the University of Siegen from an Adolf Reichwein campus building, which looks like this. So this is one of the horn antennas I was talking about, the one that is receiving the echo from the scene. And we waited until the satellite, well, they waited until the satellite went over this scene illuminating, and and this is the other horn antenna pointing at the satellite, and this is the hitchhiker system, which is a complete, almost practically commercial system. So it's built by our team, our SAR team at ZESS, but completely compact, completely a closed solution already. And this is the scene, and this is how it looks like the final imaging result from the SAR experiments. So you can recognize forest areas, areas with trees, structure, so buildings. You can recognize here a big structure, which is an industry in the reality. So this is how the optical image from a satellite would look like. So you can try to register both of them and see that there is a very good overlap. So you can even see here these beams here of the structure, which are due to the iron beams. So this steel structure of the industry that in principle from an optical image you cannot really deduce what is behind, right? So if you want to deduce the use of certain installation to check that is being used for what it should be used or what is behind, you can use, for example, SAR imaging, and in this case we were completely passive in the sense that we used a satellite that was going around to illuminate the scene. Of course, one can apply compressive sensing to SAR. In principle, one would not like to discard measurements, would not like to reduce even more the measurements because the signal-to-noise ratio is rather low in this case. But if possible, this will come naturally as a byproduct, right? So rather than that, the idea is to get more information out of the same data and, well, ask more questions and get more answers from the same set of data. And of course, if later we have more and more observations and we don't need them because we can do with less, then we will use it as redundant data for noise reduction, robustness, and, well, in general, estimating the signal better. Well, of course, as you saw the previous image, they are not sparse. Sparse means that most of if a vector is sparse, most of its elements should be 0. And the images, well, were rather dark, but no element is really 0. So you need a mixed up of different domains to attain sparsity, so an over-complete representation. So imagine, well, a Gabor dictionary, a dictionary that is rather large, but in which you can achieve a really clean representation. And also we have to find incoherent sensing matrices. So we know our data, okay, it is representable in this basis, and now we have to measure incoherently with this basis. And this is not a trivial job and not a trivial job to implement it in hardware. So classically, for processing those images, you first form the image and later segment, classify, or extract the information. But is it really necessary to do that? Can't we really work closer and closer to the sensor? Can't we really work with raw data with lower and lower dimensionality in a space that is in principle not meaningful, but from which we can extract directly meaningful information, or do we really need to follow the traditional pipeline? So probably we can jump and try to work more and more closer to the sensor. So, well, of course, another step is the integration of a priori information. So if we know things that in principle are not in the model, compressive sensing offers us the possibility of integrating it into the game. Well, we can of course combine compressive sensing with a Bayesian framework, with a Kalman filter, a particle filter, or any kind of probabilistic filter, or even try to generate a model for the sparsity. So try to model how the sparsity will change in the future according to our model of the reality. So say, well, we have this sparse vector and we expect these sparse components to move towards this or this other component, and we restrict the way that the system can behave. So in principle, when you take one of those images, you are completely blind. So you process the data and you get what you get, but you can work in a probabilistic manner and be much more robust. So that's as a general introduction. Now let's try to get more and more focused into our topic, which is compressive sensing for the photonic mixer device. So don't worry, we're going to start soft. So from the beginning of the times, we have an idea that is repeating itself continuously and that we try to avoid. So already Pythagoras said that we should make the simplest supposition that allows us to explain what is necessary to explain. So you should not develop hypotheses that are excessively complex without a reason. So you have to stick to simplicity. Well, we know that after the translation of Proclus, but in principle it is supposed to be something true, that Pythagoras wrote that. And also one of the big philosophers of the nature, Aristotle, said more or less the same, so that we shall assume the superiority ceteris paribus of the demonstration which derives from fewer postulates or hypotheses. So if you can explain it with less, why to explain it with more? So we have this idea repeating again then, and Ptolemy, which is responsible for the astronomical system that it was used for navigation everywhere for more than 1,500 years, wrong, but used, and it worked, said exactly the same. So you should consider as a good principle the one that is able to explain the phenomena by the simplest hypothesis possible. So the idea was the center of the universe is the Earth, and it was working. Then it was fine. It could be used. It was wrong, this is true, but it was working as a system. And lately, well, this is more my favorite of the others, even William of Ockham, maybe it is the most well-known, enunciated it by means of his Lex Parsimoniae, which is saying that plurality is not posed without necessity. So the nature does not often place plurality within it without a real necessity of it. If there are a variety of things, there should be a reason why there is this variety. This is also enunciated as a principle of economy, that you should not do with more what could be done with less things in general. So, well, it is translated later. It is futile, it is a nonsense in principle to do with more things what can be done with less. And this is often called the Occam's razor, which got into the compressive sensing literature also as a philosophical background to what compressive sensing does. Okay, and now the ones that were not happy with the previous, we also have Karl Popper, that for many people is like the greatest philosopher of science of the last century and one of the greatest ever, said more or less exactly the same, that simple statements should be prized or more given more importance with respect to less simple ones, because they tell us more. The concept of information, they have more information, they are more informative, the empirical content is greater, and because they are better testable. You can rather test better something that is simple than something that is complicated, which could be a closed loop, so a fallacy, so to say. Okay, So now that we have this soft introduction, we can go to the real introduction. What we do actually in life. We do 3D sensing, which is creating a two-dimensional surface in a three-dimensional domain, which is where we live. How we do it? Well, we have, of course, many sensors in the market. Since many years, we have been doing the same. So actually, laser scanners have been in development, and now we have very good laser scanners. Here we have a Velodyne with 64 channels, which is able to provide 2.2 million points per second. This is quite a lot. And the problem with laser scanners is, as usually, we have something with mechanical parts that are moving, rotary mirrors. Nobody wants that if your vehicle is moving rather hard. And also a hard trade-off between the acquisition rate, so the speed of the sensor itself, and the resolution of the images it provides. So it has to scan the scene. So therefore, you always have this trade-off between these two opposing requirements. On the other hand, the good part is that you really have a high depth accuracy, so within the millimeter range or less. So this is the option of choice if you want to be accurate and you don't care about anything else. Definitely not about the price. Because if you mount this on a car, you really have to spend a lot in the car if you want the car to be more expensive than the sensor. And well, going to more traditional things like stereo systems, we know that when they are passive, so this is very good if you want to work in certain environments where you don't want to be detected. For example, you want a passive system. You don't want a light that is like a lighthouse saying, well, here I am. You want something that is not emitting anything. And there, a stereo system is the option of choice. The problem is that you need a bulky system. You need at least 2 cameras or more. And you need a certain baseline between the cameras. The larger is this baseline, the better it is for the estimation because it works by estimating the disparity. But the more complicated it is to establish correspondences in the 2 images of the pair because the images will look more and more different. And also, well, you will have different occlusions in one image and in the other, and you will have areas where no estimation is possible at all. Lately, we have seen that Microsoft has put into the market the Kinect sensor, which was using some light coding technology, emitting a pattern of points and comparing it to the reference pattern by hardware, stored by hardware in the sensor. And this was working pretty nicely. It's in the end based on triangulation. And it was, well, it gave rise to a huge amount of work. It was mounted in quadcopters like back 6 years ago or more, and it was doing a very good SLAM work, reconstructing the indoor of buildings and things like that. We even mounted it in one of our Peer-2 robots, well, in our Peer-2 robot in the Autonomous Intelligence Systems lab in Freiburg for indoor SLAM, and it was working pretty nicely also. Okay, so this is what we have as introduction. What else we can do? We can use what is called a time-of-flight camera for 3D sensing. So, of course, time-of-flight tells that we measure time. But measuring time is complicated. If you want to build an array of sensors or detectors that are measuring time up to the picosecond resolution, you will run into a problem if you want to build really a large array of those. And therefore, we'd rather measure phase. So we have here our user that is in front of the camera, praying for the camera being eye safe, and we emit the radiation to the subject. We typically use either an LED or a laser emitter, which is modulated by this module here, which generates both the signal for the modulation and the signal for the integration. That regulates this array of detectors, whatever a detector is in principle. And of course, the subject is emitting a reflection that is concentrated on our array, and this reflection will be shifted. Okay, so this signal was modulated in principle, and now the phase shift will contain the information we want. So the depth is somehow coded in this phase shift, and we can solve it. And problem solved, we have the depth from this phase shift, this is the speed of light, this is 2 times 2 pi because you have to go and come back, and this is the modulation frequency that we all know because we are modulating. So problem solved. Typical modulation frequencies are between 20 to 120 megahertz. We work in the near infrared band. For example, ourselves, personally, we work with 850 nanometers. What are the problems? So why we had to work? Well, we have a resolution that is low when compared with conventional color cameras. So if you compare the 19K and the 41K sensors of PMD, PMD Tech is the company who manufactures them, well, we see that the resolutions are, well, definitely 1 order of magnitude lower than a conventional color camera. The Kinect sensor, the version 2 of the Kinect sensor, the newest one, well, has a higher resolution, but still is 1 order of magnitude lower. So when you try to combine both images, you run into a problem in principle. And also relatively low depth accuracy. So despite theoretically you can go down to the millimeter range, in practice, in real conditions, we are within a couple of centimeters accuracy, except done for the Kinect version 2, which really has an outstanding millimeter accuracy in real operation, but the range is limited to 4.5 meters. And here we see the output of one of our ZESS multicams. You saw it before. So this is the color image, and this is the depth image. You cannot see much because there is no dynamic range enough, but you can already see that the resolution of the image is much lower. You see it here in this Böhler star, where you cannot resolve those fields here, and you see it. You see also that the accuracy is not very good. So there is a rather noisy effects going on there. Okay, so we have the problems, and now why we think that compressive sensing can help. Well, first we have to see what we have as problem from the compressive sensing point of view. So in the case of poor resolution, why we have poor resolution? If normal cameras are so good and have so many pixels, well, we need a relatively large pixel. So the pixels are large and have a complex structure to do this phase shift estimation, and there is a relatively large blind area all around the pixel. So in the end, you have an area, a sensitive area that is very small, and a large area that is blind. So somehow you no longer are taking samples of a signal, like in the traditional way. When you sample a signal in the oscilloscope, they are real samples. In principle, you hope so. But we have measurements that are done according to a certain measurement kernel, measurement function, that is given by the pixel itself. This is the first thing to take into account. The second thing is that looking at the poor depth resolution, well, at the end of the day, you have to extract this depth. So you have to compute the depth from the raw measurements of the sensor, and this means modeling, and this means sticking to unrealistic assumptions. For example, we typically assume that the signals, both the modulation and the control signals, are sinusoidal to estimate this shift easily. And this is also wrong. So in general, in both cases, we are in the case of having incomplete measurements, noisy measurements, from which we want to extract our signals. This is where compressive sensing comes into the game, and we need to recover those original signals from those bad or not so good measurements. And for this, we need first a sparsity models of the signals we want to recover. So for recovering the signals, we need them to be sparse, low complexity, somehow explainable in an easy way. Otherwise, we cannot do magic. We will not be able to recover the signals if they look like random noise. That's clear. Second, a faithful sensing model. So we need to know what's going on. We need to know the forward transformation if you want to jump to the other side. Maybe you model it and you cannot jump anyway, but you need to know the way that you were following if you want to go the way back. This is a step 0, let's say. And finally, an appropriate recovery method that allows you to solve the inverse problem, which is an ill-posed problem in principle. It's an underdetermined problem. So 3 critical points, keep it in mind, but the main goal of the whole thing is to get depth images, to get these 3D images of better quality than before, using the same raw data from the same sensor. Okay, first of all, what we have to do, we have to look in which signal domains we can apply compressive sensing with some advantage. Once we identify the domains, we study up to which extent the compressive sensing requirements, this compressibility, this sparsity, for example, are fulfilled. Later, we develop techniques that are oriented to optimal signal conditioning in the sense that we try to push this fulfillment of the compressive sensing requirements, okay? Optimal conditioning from a compressive sensing point of view. And finally, this is the core of the work. We develop methods applying compressive sensing in these two different, well, in the fields that we will find. They are going to be two. And with the main objectives of solving the problems that we saw before. On the one hand, improving the lateral resolution of the images, more pixels, but meaningful pixels, so to say, and improve the depth accuracy, so less depth error. And or resolution. In this case, this resolution means resolving more than one target per pixel, but this will not be covered into depth here. Okay, did someone work on that before? The answer is always yes, whatever is the question. So, of course, we have a corpus of works applying compressive sensing to time-of-flight imaging. We have what was called a single pixel time-of-flight depth camera, which was a PMD array working as a single pixel camera. So with external spatial light modulator, like the single pixel camera, the initial one. So it's simply a replica in the time-of-flight case. Later, the Kodak framework, which used instead of a PMD sensor, a photodetector. And it also used spatiotemporally modulated illumination. So in that case, it's similar to the previous, and some evolutions of the Kodak framework in which this photodetector was substituted by a photon counting detector. But all these approaches, they are kind of naturally restricted to a single sensor element. So if you can build an array, despite it does not have so many pixels, why are you going to use a single pixel element and collapse the bandwidth of the system without a reason? And then we have other approaches that brought compressive sensing to the photonic mixer device somehow, and we have these transient imaging inspired approaches, so you can imagine many frequencies and many different phase shifts which are kind of probing the scene, and always kind of quasi-sinusoidally modulated light. And also light transport inspired approaches like this frequency probing here, and this phasor imaging. Frequency probing also uses many different frequencies as before, and phasor imaging uses a very convenient phasor formulation of the whole problem, in which well, the return is modeled as a certain intensity, which is, well, the amplitude of the phasor, and the phase shift is modeled as the phase of the phasor. And they make use of the fact that at very high frequencies the global light transport vanishes and things like that. So of course you can do a lot if you really have a large bandwidth in your system. And all these already take profit from an array of what is called correlated sensing elements, which are the PMD pixels. So they make so what we can contribute? Well, first of all, we have some methods for solving preliminary issues that would preclude the direct application of compressive sensing into the game. As I said before, fixed pattern noise, SBI activation, low energy operation. Later, we provide a faithful characterization, so this sensing model, of the response of the PMD pixels in spatial domain. So the 2D spatial domain, the physical surface domain of the pixel at subpixel scale. This is important. And some methods for applying compressive sensing in this 2D spatial domain where the raw images live, so pixel domain, not subpixel domain anymore. And here we provide both a compressive sensing framework for super resolution, so upscaling the resolution, and a greedy algorithm for depth error reduction and data flow reduction. So this is the other way around, so reducing depth error. And later in the other domain, in the time frequency domain, so no longer the spatial domain, we have a method for simultaneous multi-channel recovery of the waveforms that we are receiving at the pixel, and later an evolution of that, which is a complete framework for both waveform reconstruction and phase retrieval. Of course, if you have the complete waveform, if you can reconstruct the waveform that is arriving to your pixel, you can, of course, resolve the phase. That's no problem. You have full information if you are able to recover the full waveform. Now, probably for you the most interesting part of the talk, the fundamentals of compressive sensing and of the photonic mixer device. I will present first the hardware, the photonic mixer device, and later some concepts of compressive sensing theory. So, the so-called PMD pixels, or intelligent, smart pixels, are pixels that are able to sample the cross-correlation function between the signal we are emitting, the signal we are receiving at the pixel, and a control signal, which is typically the same that we are emitting, or the same shape at least. So we sample this cross-correlation function, and for this we need sequential acquisitions. So if you want to do 4 samples, that is the typical case. Typically we sample at 0 degrees, 90 degrees, 180 to 170, so X-spaced samples of the cross-correlation function. Then you need 4 sequential acquisitions. That's clear. And the pixels have 2 integration channels. So that's very beautiful to see. So you have 2 photo gates here. So you have 2 transparent terminals here on top. And of course the photons go through and collide here, and the photo-generated carriers are generated in this area here. And you use these 2 phototransparent terminals to produce a gradient in this lower area and push or pull the carriers to one side or to the other. And these are the integration wells where you are going to store the carriers. This is the silicon oxide, and this is silicon. And for this we use, of course, we need a certain potential that is relatively large, plus this differential potential that is going to control the gradient to one side or to the other. And now you can imagine, if you work in a binary operation, it will go either to the channel A or to the channel B. So you have the capability of controlling the integration. Typically, square signals, 50% data cycle. And this is how we work. And we call one channel A and one channel B. Normally, once we have the measurements, these 4 phase measurements, we have to extract the depth. And normally what we do is we apply the so-called 4 phases algorithm, which estimates the 3 free parameters, namely the constant offset due to the background illumination and the constant part of the signal we emit, of course, the signal amplitude, which is of course influenced by the power we emit and the reflectivity of the target, etc., and the phase shift. So those are for us contingencies, so to say. What we are interested in resolving is the phase shift, but we have always 3 free parameters, and the 4 phases algorithm is able to extract these 3 free parameters from the 4 measurements. In principle, 3 measurements would be enough, but this has certain nice properties due to symmetry. And what we do is an arctangent transformation. Once we have the phase, we can use the previous equation we saw before. It's just a constant transformation to the depth. But as we can see here, remember, it's an arctangent transformation of the quotient between these differences between measurements. So it's a nonlinear process. Okay, now let's go to compressive sensing. So that is how the PMD technology works. What is compressive sensing? So the challenge in compressive sensing is to recover a signal, an n-dimensional signal S, from few measurements, for example, a vector of measurements y that lives in an m-dimensional space, where m is much lower than n. So a traditionally ill-posed problem, a problem that is impossible. Now, compressive sensing requires, first of all, a linear sensing model. So we need to model the whole process as a linear transformation, which is a matrix. So we need a sensing matrix here. Is, as you may see, is a wide matrix. So it's a matrix that has a number of rows much lower than the number of columns. So an underdetermined system. And of course, we have certain conditions for recoverability, and we need, for the signal to be recovered, we need that the signal is sparse. We saw it before, or compressible. That means that the k-term approximation error decays, the compression error decays very rapidly with the compression rate. And this, we model it as the representation with this dictionary or representation basis, which we denote by psi. And this x here is now the vector of sparse coefficients. So it's a vector in which most of the coefficients are 0. Why? Because in the real world, most of the signals are not sparse. If I see around, nothing is sparse. I don't see 0 signals anywhere. But I know that there is some structure behind. I see that not everything is random noise. Therefore, there should exist a transformation that transfers this real world signal into a sparse signal. And this is accomplished by this dictionary here, which in the easiest case is just a basis. So it's an orthonormal basis, for example. And later we can construct this measurement matrix, which is just the product of these two, and work directly in the sparse domain. So see the system, vector of measurements, matrix, measurement matrix, a sparse signal. This is what we will see all the time. There is nothing else than that. And now we also need a certain incoherence requirement. So the sensing matrix psi has to be incoherent with the dictionary. Why? Because if we measure in a coherent way, then we will have to make all the measurements to check which non-zero coefficients are firing, so to say, in which ones we have signal. Therefore, we need to measure in a way that we sample all of them in each measurement, and in each measurement we have to get more and more information, so they should not be redundant. This is a trade-off. How we can measure coherence? Well, this is a traditional or more or less commonly accepted measure of the coherence between sensing matrix and dictionary, which is mostly the maximum of the absolute value of the scalar products of the rows of the sensing matrix and the columns of the dictionary. So how we sense, sensing functions, how we represent vectors, columns of our bases. And this has to be as close to 0 as possible, so as far from 1 as possible. Okay, of course, those are rather heuristic conditions. Now we have to see, well, what are sufficient conditions for recoverability. We have some RIP-free or null space-based, so to say, conditions for recoverability, which are based in null space of the matrix A. If you remember from algebra, the null space of a matrix is the subspace of all the vectors which are projected to the vector 0 through the matrix. Okay, so this says to us that if we have that the square root of the sparsity is the L0 norm of the vector we want to recover, is lower than this, then we will be able to recover the signal. And this is the minimum of over all the null space vectors of the quotient of 1/2 the L1 norm over the L2 norm. And what is this saying? This is saying that the energy of the null space vectors should not be concentrated in few coefficients. They should not be sparse. And this is because we need that differences between sparse vectors that are sparse should be transferred untouched or very properly through the matrix. If those were contained in the null space, would be projected to 0, and you cannot measure. Okay, so it's very intuitive. Here it looks a little bit complicated, but it requires a certain spread within coefficients of the null space vectors. Okay, and on the other hand, we have the very well-known restricted isometry property. Don't worry, this is very simple. It's just saying that we are preserving the distances, L2 norm distances between the vectors. So if we have that, let's enunciate it properly, the RIP condition of order k is said to be satisfied if for a certain constant, restricted isometry constant delta k, which is between 0 and 1 but should be close to 0, we have that this holds. And this, you see that is mostly 1 when this goes to 0, this will be mostly 1 when this goes to 0, so it forces to keep the L2 norm untouched of these x vectors. And we have that recoverability is ensured if you fulfill the RIP of order 2s, 2 times the sparsity. Why? Because differences between s sparse vectors are maximally 2 sparse. if the coefficients are not aligned. Therefore, it means that you are preserving distances between S-sparse vectors. Okay, so you preserve the geometry of the problem. And this is crucial. If you are able to do that, then this matrix A is preserving the geometry of the problem, and you will be able to solve the problem despite it's an underdetermined system. Okay, there is no more magic, and later, of course, recoverability means that you can solve the problem by convex optimization. So in principle, you should solve this problem. So between all the possible solutions, you should try to find the one with minimal L0 norm, because it's your requirement. You want a simple solution, because Wilhelm von Ockham already said that, and you have to do this. So you cannot solve this problem because it's NP hard, so you need non-polynomial time to do it, and we don't have it. And at the end of the day, you have to solve the convex version of this problem, which is the L1 minimization, because the L1 ball is the convexification of the L0 ball. The L0 ball goes to the limit like this in the edges, and the L1 norm is more well behaved. Okay, so that's done for fundamentals. Now let's see how we do the real work. So first of all, we have to solve several problems. We have this fixed pattern noise, and the fixed pattern noise, everyone that works with sensors knows, is due to, well, differences between the different pixels, and in this case also because the different offsets and gains of the ADCs. So you end up with something like this. So you cannot see there probably from there this image properly, but it looks like you are getting into the matrix. So you have many columns there, and many high frequency artifacts that are not natural. And at the end of the day, this translates into, well, here we are looking at the Dobechis 4 wavelet coefficients of this image, and we see that the image cannot be said to be really sparse, because this cannot be said to be the negated of the support. There is a non-zero component all around there. Therefore, well, the signal is not really sparse. Those coefficients are not zero. And also, is compressible? Well, maybe not, because is this a quick decay? We said that for compressibility, we really need a quick decay. This is not rather quick. It's a decay anyway. Well, we solved the problem by per pixel linear calibration, and this is what we get. So we get rid of this fixed pattern noise related high frequency artifacts, and the important part here is to see the effect. Okay, so we see that now we have a really quick decay that is characteristic of compressible images, and we can say that this is the negated of the support, because all the coefficients here are, well, the complement of the support, because all these coefficients are within the noise level of the sensor. And is this important? Does it have an effect? Yes. So those are already recovered raw images. So are images that were reconstructed with 50% of the normal data. So the raw data was projected to a subspace, well, to a space of a lower dimensionality, and later reprojected back or reconstructed using minimization. The projector was a ±1 binary matrix derived from a Hadamard matrix, so not random but randomized. And the dictionary was a Dobechis 4 orthonormal basis. This is the result if you work directly from raw data. So you cannot recover the image. You cannot go back to the original domain. Why? Because you did not fulfill the requirements. But if you work on calibrated data, we see that there is an exact reconstruction throwing away 50% of the data. So you will be freeing 50% of the bandwidth of your system in principle. Okay, next problem, the suppression of background illumination. This is actually a solution, not a problem, but typically solutions generate a manifold of new problems. And the SBI is a system for suppression of background illumination. So we can see that background illumination will eat up the dynamic range of our pixel, and we need to subtract it. We need to remove it there to avoid saturation. So this is more or less how it works. This is the area where you want to be, and you never are. The linear area where your pixels are integrating properly, and at a certain point, one of the channels is approaching saturation. The SBI starts to be active. It removes a constant current from both of the A and B integration channels. so that the most charged channel remains constant, and the other decays so that the difference of the slopes remains constant. Okay, so it doesn't matter anymore what is your exposure time. The measurements will be right. This difference of measurements will be preserved, which is what you want. The problem is that nothing is perfect. This is a capacitor that is being discharged, and you cannot go like this. And of course, as it gets discharged, this is no longer a straight line, and at a certain point anyway, sooner or later, you will get that this goes close to zero, and you cannot break through zero, and you will be already here. One could say you are within the SBI limit, and you will not only have very noisy images, but wrong images. The depth image will be wrong. The values of the depth will be not valid anymore. How does this operation affect to our case? Well, in the conventional operation for relatively low exposure times, everything is fine. This is a scene of a relatively large dynamic range, a corridor, longitudinally focused, and we see that we have a nice decay. Most of the coefficients are below the noise level of the sensor. Well, problem here, if we start increasing the exposure time, we start to work in this area here, we see that the SBI gets active for some pixels there, and we lose compressibility, we lose sparsity, and these lines move towards the left. And if we really go to large exposure times, we start to recover a structure here, a door, there is another light here, cannot be seen here, but there is. And you already get some pixels that are on the limit, that are here. And you really get very noisy images, noisy raw images, which you will not be able to process in a compressive sensing friendly way because you are really losing sparsity there. So what we did was to develop a certain technique, which was an adaptive high dynamic range technique. Everybody knows nowadays high dynamic range acquisitions for conventional cameras, for your mobile phone. It simply takes several pictures and combine them in a way that it extends the dynamic range of the final image. We did it in a more sophisticated manner in an adaptive framework that adapted a set of short exposure times to the foreground object. So the object causing saturation that was coming into the scene, a car, a person, whatever object very close to the camera, plus the acquisition time of the background. So we can see, if we, in this scene that we saw before, you remember those are Euler stars, are calibration targets. You see that if you adapt the exposure time to this panel here to be perfectly illuminated but not saturated, you lose the background. Okay, this is what is called a disaster. And if you get an exposure that is higher, you recover the scene very accurately, but you cannot see it here. But I will tell you that here you lose completely the estimation, and you start to see effects of the SBI. So you start to see this salt and pepper noise there. If you perform an intensive HDR, you solve all these problems, and we saw that our approach is even slightly better. And furthermore, we got an increase of lateral resolution by a factor of 3. So those targets are used to estimate the lateral resolution, the effective lateral resolution of the sensor, and we were able to recover those targets with 3 times more lateral resolution. Okay, problem solved. The last one, operating in very low energy conditions. This is important, as I see, because in some applications you will need it, or it will be a requirement. And in those cases, you have that your measurements are samples of a Poisson distribution. And a Poisson distribution is not a nice distribution because you have that the variance of the random variable coincides with the expected value, which is the parameter of the distribution. And of course, we have traditional variance stabilization techniques that can be used to help on that as a pre-processing, and we have classical denoising techniques like bilateral filtering that can be applied, and they work up to a certain extent. And work has been done on that by Benjamin Langman and in our group. And mostly a bilateral filter integrates both spatial proximity, so proximity within the pixel domain, and intensity proximity. So intensity means, well, the value of the pixel in our case. Okay, similarity. What it was done, it was mostly for detail transfer and upscaling. Why? Because those images, the RGB images, were high resolution, the depth images were low resolution, so the idea was, well, can we actually perform a joint bilateral filter in order to transfer the high resolution detail of these images to the depth image? The answer is yes, it was working very nicely, and those weights were applied to a filter working on an upscaled version of this low resolution image, and we could really transfer detail. The problem is that you are relying on hypotheses that are false. So you do not have this correlation between depth and RGB. Those are modalities that could be isolated. If you are in an office that is full of posters, they will be rather isolated because the posters are, well, definitely high frequency, definitely structure in the intensity, but are playing in depth. So it is more meaningful, and this is what I did in the past, to filter in the raw image domain. So we have a set of raw images. So all this time-of-flight imaging works with sets of images in order to estimate a single depth image. So we can process them simultaneously to compute unique weights that are going to be applied to the filter, to each of those raw images, and generate a set of joint bilateral filtered images that we can use as the previous. We can use them to generate the depth images. This is what we got. This is definitely not a mistake. So we were able to go up to the microsecond range in conventional operation. And this is what you will get simply taking the first set. So as it goes from the sensor, you compute the depth. This is what you get. Depth image. Those there here behind, you have variabilities of several meters. So it's rubbish. If you apply a conventional filter over this, it will smooth out all the detail and the measurement is completely meaningless. If you apply this filtering in the raw image domain, we see that, well, the depth value is actually not so meaningful still, but you could use it for segmentation purposes or at least foreground segmentation, things like that. You don't have jumps of meters as before. Already with 20 microseconds, we see that the results are very nice already. Well, you can use it for measuring, and for 50 microseconds, the results are even better than with conventional exposure times, because this pre-filtering really removes a lot of noise that is present in normal operation. So 3 problems solved. Now we have grounded more or less all these problems that we had before, and we are ready to deploy top our compressive sensing machinery. Okay, so we solved the preliminary problems, and now we can recall what we needed. So you remember I said we need linearity of the measurement model, we need the sparsity of compressibility of the signals, and we need this incoherence between sensing and representation. Okay, we already get the first problems. First of all, what I said, we have a very non-linear sensing model. There is no way to linearize that. I mean, you can linearize it, but together with the fact that you have noise, this is a non-linear noise amplifier, and is the best way to go to the hell. So there is no way to linearize an arctangent of a quotient. So you cannot linearize the complete measurement pipeline. And therefore, we are forced, or better said, we are recommend to work in the raw image domain. And this is what we are going to do. And there we recognize 2 domains. We said that we were going to look for them. So we have the spatial domain, where the raw images live. People who work with images know they are compressible in Fourier bases, but there is this lack of spatial resolution of the Fourier bases. DCT, so locally centered, and wavelet bases in which you have real localization. So in all those domains, we can apply compressive sensing in the spatial domain, and later in the time frequency domain, well, depending on the system you have, you will always be sparse in the time frequency plane, because if you were dense in the time frequency plane, you will be a random noise generator. Therefore, in pulse systems, you have sparsity directly in the time domain, so you are emitting signal within a certain time and all the rest is 0. And in amplitude modulated continuous wave systems, like our system, we are sparse in the frequency domain. So we emit with a certain restricted bandwidth and all the rest is 0 in frequency. And in general, we should exploit the sparsity in some more general region of the time frequency plane. So we simply have to recognize in which region we are working. So now to the fun. Let's model the whole thing. So let's go to the lab, break a sensor, and look inside. So we removed the infrared, well, the daylight blocking filter of a commercial PMD 19K S3 array. We took a picture, and this is what we see. So in principle, a person that is not familiar with the technology could not even see what is a pixel. So a pixel is actually something like this. Okay, this is a pixel. But we have areas that are metal shielded. This is metal shield all around, and this is also metal shield, and areas that are, well, silicon, something. But we in principle do not know what they are doing. So we take a fluorescence lifetime imaging microscopy of the sensor to see which areas are actually active, and we see that the areas that are not black are active areas. If we perform a kind of segmentation, we see all that is white here is an active area. So photons hitting these areas may be integrated, may be also lost, but in principle, photons reaching the black areas will be for sure lost. If you are working in imaging technology, you know that this is not like an imaging chip should look like. Probably we are losing a lot of energy there. And actually, we are losing 69% of the energy that is reaching the chip because it's blind, this area. And also we have two different kinds of pixels that are alternating every second column. We call pixels of type left the ones with the readout wires at the left, and pixels of type right the ones with readout wires at the right. And in principle, we need to model that. So we need to model, if we want to aim for super resolution, we need to model how an infinite or high resolution signal, a high resolution image, gets from the high resolution domain where it lives to the low resolution domain where the images we have live. We have a low resolution image, not the original one, and we want to come back. So you need to model the forward process, and this is what we try to do. And this is our phi, so our sensing matrix, which models that, both for the channel A and channel B, okay? You can forget about the gammas. This has to be done for each of the channels. And this is an operator modeling the optical process, so the optics that are in front, so objective, filter, and so on. So it's mostly a smoothing operator. And this is going to model the spatial response, so the response in the 2D domain of the pixel. If you had a pixel that has a constant response, like it should be a photodiode, for example, then you could use a constant model, and this would not exist. Okay, it will be an identity matrix, and you will be measuring real samples of the signals, average samples of the signals, and then you could use the typical model of Gaussian smoothing plus regular decimation, and you will be done. But this does not seem to be the case, especially if you aim for larger super resolution factors, because this is just a dummy, naive model from what we observed. We did something like this, and we said, well, okay, from super resolution factors that are 2 or lower than 2, the model does not matter because the symmetry of the pixels already does the work for us, and it is completely equivalent to have a constant response. But if you want more, then it is not naive, and you really need to model how the pixels are integrating the photons. Otherwise, you do not know the forward transformation. And this is the cases where we are going to be interested in. And how we can do that? Well, we can go to the lab. Well, we were already in the lab and try to generate a sacrilege, so a kind of customized camera in which we mounted here a PMD front end. So here is the chip. Here we have one of our multicam backends. So this is what remained from the multicam, where the FPGA is, and so on. And this is a microscope probe holder. So this is what is mounted in an inverted microscope. And this is just for the lenses of the microscope to go through. Hardware, well, this we already said, with a stepper unit for displacements and a laser for hitting the sensor, 477 nanometers. This is the reason why we had to remove the infrared filter on top. And this is how it looks like. We mounted in the inverse microscope. We have the laser circuit under it, and those are lenses which we use to focus the laser with a very narrow beam on different points of the pixels. And what we did was to do this for different points of the array or of the pixel and surrounding area, and simply record the responses. So record with what we get in the channel A and in the channel B in each of the measurement points, and we repeat the process, illuminating exactly here in the pixel, and so on and so forth. And if we do that with enough samples, with a grid that is dense enough, then we are going to end up with a complete, discrete, but dense response of our pixels, which will probably, maybe, look like this for the channel A and look like that for the channel B, maybe. This is reality. So these are the results we obtained. So measurements from the channel A and from the channel B, making an image for what we obtained at each of those points. Okay, those are not photographs; they are just those results we were talking about before. And for visualization, I subtracted the A minus the B channel. Okay, so things that are red here are mostly response in the A channel. Things that are blue and mostly response in the B channel, so that the difference goes to negative or to positive. So this is for a pixel of type left, this is for a pixel of type right. So you see you can hit areas of other pixels of the array, and of course there is no response in that pixel. This is in principle good. And you can hit areas, well, you see that if you hit here, the photon will contribute to the A response, but never to the B in principle. So you should expect, if you work in DC, as we worked for this experiment, that everything is green, but it's not. So it means that there is a correlation, there is an influence of the position where the photon is arriving on how it is being integrated. This is of no importance because this for the normal operation of the pixel, because somehow you, let's say, you multiplex the operation in the spatial domain. But it is of importance if you want to go beyond and try to super resolve the image. Otherwise, you don't know the model. And later on, what we can do is to restrict this range and see how the image is saturated. And if we really restrict the range, we see cross effects. So we see that if we shoot photons at this pixel here that is next to it, we get responses, very weak responses, but we get responses in the pixel we are measuring. So there is crosstalk between PMD pixels, and one can at least observe it using this experiment. So this is the position of the pixels, 45 by 45 micrometers, very large pixels in principle. Okay, and now we can go further and add an additional dimension and try to use modulated light and raster the phase shift. Okay, so make a sweep analysis on the phase shift and see how the pixel is working. Okay, this allows you to see somehow how the pixel operates. So focus, for example, at the zero phase. Now we are going to arrive to 180 degrees, in which we expect that everything gets integrated in the B. But you see, there is still some remaining part there. So not everything is blue. It means that if your photon is hitting exactly there in the pixel, it will be integrated in the A, despite you set to the pixel, move everything to the B. But the modulation contrast is not 1, and you have these problems. Now we are getting to 360, that is the original 0, 1, and therefore it should be everything integrated in the A, but you see here there is an effect of a certain non-zero value that has been integrated in the B. Okay, now just for fun, we can integrate those responses along one of the 3 dimensions or 2 of them, for example, along the spatial dimensions in 2D, and it remains only the phase, and we can see how those signals are. This is A, this is B, this is A minus B, so it means that we are dealing with a triangular behavior. So we are dealing with a cross correlation between more or less square signals. So they are not really sinusoidal. And one step further, we have the measurements, which are samples of the cross correlation. We can decorrelate. We can make a deconvolution with a theoretical light signal. It was a laser, so it was a relatively clean signal, square. And if we perform a deconvolution with this signal, which is a square, up to the discretization, we get something like this. So it means that the control signals are more or less trapezoidal. Okay. And furthermore, if you extend this to a wider range, those are also cropped ranges. to see the crosstalk effects. If you extend it to higher ranges, you can observe medium range or long range crosstalk between PMD pixels. So you see there is no crosstalk between the pixel of interest, which is placed here, and this one. For example, you can shoot here and nothing will happen to the response of this one, but there is a slight crosstalk between this pixel and the pixel of interest, and we can observe these effects differently for the A and B channels and for the pixel of type left and of type right. And what one could do, for example, as a demonstrator, will be to model this crosstalk effect as a convolution with a certain crosstalk kernel, okay, and try to deconvolve. And we did it. It's published here. So we decrosstalked the image a posteriori. Be careful. It's a relatively tricky thing, because if you have noisy images and you deconvolve with this kind of kernel, well, you amplify the noise, okay? But since it is a very soft kernel, so to say, and also it practically only affects to the edges, you only get a correction at the edges, and the results were relatively nice. But this is a different story. Where we are focusing it is in getting these responses, these 2D responses. And this is what we have now. So we have already one of the main requirements of compressive sensing. We have our sensing model, which is modeling the transition from the high resolution domain to the low resolution domain. So one of the biggest stones, we have it there. And they look like this, and these vectorized are the rows of our sensing matrices. So we know how our system is measuring. Now the next big stone is the representation. So we have to know how we should represent the signals so that they are sparse. And for this we need to find an optimal basis. We see that a Fourier basis works very nicely for compression at the beginning, but it never goes to zero representation error because of the lack of localization of the basis. And if we use wavelets, hard wavelets, major wavelets, Dobechis wavelets, doesn't matter, the results are the same. Very good results. Those are for the 8 raw images, so 4 raw images for the A channel, 4 raw images for the B channel, and all of them behave equally. And one could take this wavelet representation, or, for example, try to recover using bounded total variation, which is more or less a sparsity in some more general gradient domain, and we already have the whole system mounted. Now we can go to the work and bring compressive sensing into the game. Okay, so of course, if we want to super resolve, to upscale, we saw those nasty blind areas. Of course, if we never got any signal from this area, we cannot reconstruct what we never saw. That's clear. Therefore, we will need several different images, fewer than what we will need for traditional super resolution. So if we want to resolve an array of, or a super resolution factor of 9, so 9 by 9 pixels per pixel, we will not need to measure 81 times, but we will need to measure in some different positions in order to cover the whole domain, okay? One cannot do magic, okay? That's clear. And and this is written here, and for this we move the PMD camera, or we move the sample from with respect to the camera in order to generate further synthetic PMD cameras, which we will model here as K, okay? So this is the same model as before, but for each one of the cameras with a different displacement, and the effect is only changing this PK, okay? So the kernels, the sensing kernels, will be displaced with respect to the previous. Okay, there are 2 options to do this. The best one is pseudo-random displacements, which is the most compressive sensing natural one. So you just take M measurements according to some M different pseudo-randomly chosen displacements, and the problem is that it's slow in the acquisition because of the system of this step per unit. It works very nicely with stepwise acquisition, but it does not work so nice if it has to go to a completely different point. And this enables compression at sensing, so you don't need another process afterwards. But what we finally did was a regular grid of displacements, so we acquired all the points, and later, which enables a very fast acquisition, and later, and is very repeatable, and later we compressed. So we we compressed right after sensing, so to say. Okay. And here we have the whole thing stacked. So the only thing that changes are this phi matrix. Sorry, the P matrix. The phi is the composition of the previous for every k, where k goes up to the number of displacements. And this is the pseudo-random projector that we use for dimensionality reduction. And these are the different p's stacked one over another, and by abuse of notation, we call this again P gamma, as it was before for the case of one single camera. Okay, and there we go. So we have everything we wanted. If we take all this phi plus the sparsifying dictionary together, we have this A gamma, which is the A matrix we wanted before. So we have our complete measurement matrix. And now the dimensionality is this n sub, where sub is for subpixel, which is higher. Is super-resolution factor times the original number of rows times super-resolution factor the original number of columns, which is therefore super-resolution factor square the original dimensionality of the problem. Okay, does it really work? Surprisingly, yes. But for the projection, we used a Hadamard-derived binary pseudo-random matrix as before, but for the sparsity basis, we tried with the Dobechis 4 wavelet basis. But the problem is that you saw the sensing kernels before. You saw how they look like. So they are highly correlated with some of the elements of the basis. Therefore, we do not fulfill this requirement of low coherence between the sensing and the representation, and therefore it cannot work properly. And in the end, we exploited the sparsity in gradient domain. That means we perform a total variation minimization without explicitly modeling the dictionary as a reconstruction method. And this is what we get in a case of a study that was fluorescence lifetime imaging microscopy. So this is a cellulose sample, so paper. And we see here, this is our low resolution, so to say, region of interest. We cropped it from a PMD phase image of the whole story. And you can see here some of these elements of the cellulose, some of these components, but it's not so easy to resolve them. And in the end, if you take all the measurements, this whole array of 9 times 9 or whatever super-resolution factor times super-resolution factor measurements, and you perform least squares with all the measurements, with a number of measurements that is equal to the dimensionality, then you get this. So this is the best solution in least squares terms. And now we see how far can we go with compression and still recover the image more or less properly. So we see that we can easily go to reduce the data up to a factor of 2. So take a number of acquisitions that is 2 times lower than the one that we will need for that super resolution factor, and still resolve nicely this cellulose structure that we could see in the original one. I don't know whether you have dynamic range enough to see it, but it was more or less properly resolved. Okay, now this is the super resolution part. So upscaling. Now the other part is with the same amount of measurements. Can we reduce the depth error? Can we reduce the data flow? For this, we developed a greedy algorithm that takes into account several points that were not taken into account before. These crucial signal considerations are: the PMD raw images are not only sparse. Every image is sparse, but our images are a little bit more than sparse. They are k-joint sparse. It means that if we stack the vectorized images in a matrix by columns, joint sparsity or k-joint sparsity would mean that the the cardinality of the joint support of this matrix would be k, with joint support of a matrix defined as the union of the individual supports of the columns. What it means, if k is more or less equal to S, it means that they share the same sparse support. And this is a very strong condition, and that should be taken into account. Later on, the distribution of the sparse coefficients is not completely random. So we do not know where the sparse coefficients are, but we know that they have to follow a tree structure that is induced by the wavelet dictionary. If we exploit representation, well, if you exploit sparsity in a wavelet domain. And last but definitely not least is that this matrix composed in this way has a rank that cannot be higher than 3. One can already intuitively see that if you think that there are only 3 free parameters. So there are not more than 3 degrees of freedom, and therefore the rank cannot be greater than 3. So we have 3 restrictions that were not implemented before, and for this we developed a specific ad hoc developed algorithm for taking into account that in the recovery. So the measurements are performed like before, randomly, for example, and now we recover the image from this y vector of measurements, or matrix in this case, because we do it as a block of all the raw images simultaneously. And I will not go through the algorithm, of course you can go yourself if you want, but it integrates both the multi-scale operation that exploits this wavelet structure of the game, and this rank is implemented here by an SVD decomposition of the residual that is of course now a matrix, and preserving only the 3 most important columns in this case, and later a joint support element selection that happens here, in which we do this, we exploit the joint sparsity somehow, because the sparse, the indicator of the sparse coefficient, so this is just an index, is selected taking into account all the set of all the images in the set, because this is a matrix. It's no longer a vector like usually, so you are not looking for the highest correlation between each of the columns of your measurement matrix and the residual, but you are looking at the L2 norm of the product between this vector and a matrix, which is a modified residual matrix, so to say. So you implement all this in this algorithm, and the result is, if you compare it with conventional single measurement vector L1 minimization, this multiple measurement vector approach that we called structure and rank aware order recursive matching pursuit, so a greedy approach, you can see, if you compare both, that is always superior to the case in which you do the recovery image after image. So you can do much better processing all things together, taking into account these peculiarities of the data, than doing it separately as if they were independent images. Of course, one heuristically you can already think about that, but you really have to go deep into the implementation, into these details, and transfer it to the implementation in order to get a real tangible result, like in this case. So if you look below, you see that we got a reduction of the root mean square error in depth domain that can go up to almost 50% reduction. You see that this wall behind is pretty clean, and you still preserve high frequencies and sharp edges there, so there is no problem of missing frequencies. Okay, here we don't have compressive sensing anymore because the compression ratio was 1. Here we have a very strong compression ratio, but we really don't clean much the noise if you compare it to the original image, and therefore we can play and look for custom trade-offs between depth error reduction and data flow reduction. And still, you can go here, you will have an image that is cleaner than the original without no compression, and you still would be reducing the data in a factor of 2/3. So you are, sorry, 2/3. 3/4. So you are doing both things simultaneously. And finally, the last thing that I'm going to present is the time frequency domain. All that was in the pixel domain, so image processing, if you want to call it like that. And now let's go to the time frequency domain, and let's try to recover the waveforms that are reaching the pixel. So we have a certain signal, optical signal, that is reaching our pixel. Now we will try to recover the complete waveform. Once we have the waveform, we also have the information on the face. The cleanest way to do it, or the easiest, we put, just for trying, we put a delay generator completely externally. This is a conventional PMD imaging setup. So a PMD front end. We have the LEDs here that are controlled by the same control unit. Infrared LEDs, the scene, the reflection, and the PMD pixel here performing the cross correlation, which is also controlled by the reference signal. And we put simply a delay generator here, which is controlled by this external PC, a control unit, and we simply measure at different delays. And from measurements at different delays, we can completely recover the signals. Why? Because you can see that those signals, this is a real signal in blue, and this is the DCT representation in red. So you can see that with 10% of the DCT coefficients, we can completely recover the signal. All the information is there. So here in green, you have the reconstruction using only this part of the DCT spectrum. So you see that this is just to show that they are very compressible signals. And that's why we can recover them. These are the results. For a discretization, a number of discrete steps of 32 steps and 64 steps for the whole period of the signal, is a periodic signal. We have a reconstruction that is pretty good for that discretization level. If we go to further levels of discretization, so to 128 and more steps, we get problems. Why? Because in the dictionary we are getting high frequency elements or high frequency basis elements for which we are not performing good enough measurements. So we cannot see those frequencies and we are trying to reconstruct them. So using this discretization means trying to recover frequencies that we are not seeing. And this is because our sensing scheme is not optimal. So using a certain waveform that has a certain spread in frequency but not so much, and displacing them to one part to another, from one part to another, is not an optimal sensing scheme. But we get a result that is more or less okay. For example, for this case of 64 steps. So we can play around and see how good we did it. So if we recover the energy properly, we can simply compute the root mean square error. The root mean, the root mean square value of the signals, not the error, and compare it to simply summing up the A and the B channels. If you sum up the A and the B channels, you get the whole energy that was integrated there. And this is the A plus B image, so an intensity image. And this is what we get if we compute for each of the recovered waveforms. We recover one waveform per pixel. So for each of these pixels in this image is the root mean square value of the recovered waveform. And we see that there is a good match. Okay, so at least in terms of energy, we did it relatively well. And further evaluation could be, for example, well, let's have a look at how distorted those waveforms are in comparison to a pure sinusoidal. So let's have a look at the total harmonic distortion. And this is this image here. So blue means a total harmonic distortion close to 0. That means a signal that is very close to sinusoidal, good for us. And these areas here means a signal that is not so good, so it's distorted, like this one, for example, here. And this is because in those areas here we have many emitters that are interfering with each other, and by interference the high frequencies vanish. That's normal. But in areas that go to the sides, we don't have this situation, and the high frequencies are not vanishing, and we have really high harmonic distortion. And a further effect would be, for example, see that here we have an area that is poorly illuminated, okay? And this can be observed when we recover the signals, because the amplitude of the signals is very low. Furthermore, we can recover the phase shift. Of course, we have a lot of noise, mostly due to discretization, so we have jumps, discrete jumps there, but we can already see that our illumination system is superimposing a certain offset in phase. So certain emitters that are placed in this area of the camera are somehow delayed, or in this case, no, they are not delayed. This one will be delayed with respect to those others, and therefore you get a different depth. So if you start measuring, it would mean that this lack of synchronism in your illumination system is superimposing a certain pattern in depth on your scene, and this can be, for example, calibrated. This was done and it was published. I think we have the publication there. But a further evolution will be, well, do the things properly and measure properly. So you cannot expect that simply moving the signal around you are getting good sensing kernels. So why not generating really good sensing kernels like pseudo-random custom codes that you are able to design as measurement kernels and measure this signal according to these sensing functions. And this is what we did. We kept things easy for the illumination system. We have LEDs. They cannot do magic, so modulated at 20 megahertz maximally, working properly, generating those signals, rising and falling times that are non-negligible but more or less sinusoidal. That means a very narrow frequency bandwidth. But on the other hand, let's push the PMD pixel to work up to the limit of the bandwidth, or better said, let's push the control system more than the PMD pixel and generate those codes in which the maximum length of the code is going to give you also the ratio between the clocking frequency and the frequency of your illumination control signal. So you have to keep this trade-off in mind. And from now on, it's exactly as before. So we receive a certain waveform that is delayed by the scene at each of the pixels. We measure M cross correlation or correlation measurements according to different codes, M different codes, and we sparsely recover the frequencies according to a certain frequency dictionary. And furthermore, we made use of the fact that the S non-zero frequencies are the first S frequencies. So if a frequency is non-zero, then the previous frequencies are also non-zero. So it means that we recover the S equal to M more or lowest frequencies. And we have back our signal perfectly reconstructed, and now once we have the signal that is relatively clean, we can even try a multipath or a multi-target phase shift estimation. If this signal were perfectly sinusoidal, you cannot resolve more than one target. You have no bandwidth. It's impossible. If this signal is non-sinusoidal, in principle, you could try to resolve more than one target per pixel. This is what we did, and here we have now the recovered signals do not look like before. These are discretizations that are already competitive, so I think we did 720 and 1440. That means 2 or 4 discrete steps per degree, per decimal degree, and we see that they are pretty fine for M8 frequencies, 16 frequencies, 32 frequencies, which are equal to the number of kernels we used for the measurements. We have something that is good enough for estimating phase shift. This is what we did. In this case, everything is synthetic, but everything was synthetically generated from real data. So both the illumination signals were real, the scene was real, so the phases used to delay them were really acquired. This scene existed in practice, we acquired it, but we synthetically added this panel here, which is the same waveforms, well, of course, scaled and delayed according to a different phase, which is the phase of this panel. So a constant phase for all this area here. And of course, if we try to resolve one single phase for each of the waveforms, we get this. So we get phases that are in between the foreground object, that is a translucent panel, and the background object. We cannot resolve. But if we suppose that what we are getting is a superposition of two reflections, we can solve the problem, because the bandwidth is non-zero. And a superposition of two signals which bandwidth is non-zero is in principle unique. So the problem is that if they were sinusoidal and the superposition were between sinusoidal signals, you cannot distinguish whether there is one single target at a distance that is in between, or two different targets at distances that are the same distance from the central one. And therefore, this frequency spread was what we used to resolve the two different paths. Okay, and here we can see the object behind without the object in front, and resolve the object we have in front. This is important. as important as it is if you have an autonomous vehicle that is stopping before crashing in front of a glass. Okay, that's all. So we will see more or less what we saw before. So the core thing was applying compressive sensing theory to the photonic mixer device in order to improve the quality of the depth images. We saw that, well, we could use a per pixel calibration in order to increase the compressibility of the images of the raw data by eliminating the fixed pattern noise, and this was very useful. And also we presented an adaptive high dynamic range framework that avoided this saturation and this beginning of the suppression of background illumination system that was corrupting the raw images. This was also important, and we saw that we can really force the system to work in low energy operation and apply a joint bilateral filtering to largely reduce the photon shot noise. And later in the application part, in the real work, we have an empirical characterization of the PMD pixel response in the 2D spatial domain. And we use this characterization for a super resolution framework in which we were able to resolve up to a super resolution factor of 9 in a film case of study. And later in the other part, in the part of depth error reduction, we saw a greedy algorithm that was proposed in order to get attractive trade-offs between depth error reduction and data flow reduction. And finally, in the time frequency domain, we saw we presented a framework for reconstruction, so waveform reconstruction and phase retrieval that, in principle, since it recovers the complete waveform, can be used to estimate the shift and estimate more than one shift, more than one return per pixel. That was all, and thanks for your attention. If you have any question, I will be happy to answer.
Okay. Paula had to leave, so he left me here. So does anybody want to make a question here? Everything is clear. I mean, just let me make a comment. Our collaboration with Miguel and with ZESS came from some time ago. We tried to ask for a Marie Curie, and then we didn't make it because at that time Miguel didn't have his thesis ready. And then later we tried what we call an European training network. We didn't get through, but we were pretty close. We had 90 points out of 100, and they were funded from 95 on. So we were about to get it, but it was not so. So I think that we're trying to do this, to do the same. I mean, to go for again for the ETN in January. This is the deadline, and then another closer cooperation is with Julio. Julio Yade defended his thesis some time ago, actually on April 24th. And so our idea is to redesign the chip, submit another chip of time of flight, okay, and if possible to cooperate to, you know, to apply Miguel techniques, compressive sensing techniques to this chip. And actually he's here, he's been here for 1 month, giving us some chip specifications to, you know, to have a better cooperation. So we already talked about this, and I have no special questions. So Eduardo, I don't know if we can use the microphone. It seems that this is being broadcasting everywhere. So.
Everywhere.
Everywhere. Sounds wide.
Well, thank you very much for your interesting talk. I think that you're, I mean, this is the work done for your PhD thesis, right? Yeah. I think it's impressive because, I mean, you really, I mean, face different problems. I mean, not only practical problems, but also theoretical problems. I mean, the application of compressive sensing, and the facing the problem that you have to first compress the signal and also reconstruct the signal. So it's like a multi-objective problem. So thinking this in this way, I think it's very important. I mean, it's very I think it's very relevant for for the field of image processing, and not only for image processing but also for visual neuroscience too. I mean, we work in visual neuroscience. So my question is, well, I would have several questions for you. I mean, we could talk for a lot of time. I mean, discussing about issues and other things that after your talk. But the first thing is when you present the CS, the compressive sensing theory. I mean, I've read about this some time ago, and it seems to me that there's like a core that is very similar to independent component analysis, to ICA.
Yeah.
So my first comment is on it. I mean, can you discuss which are the similarities and differences with ICA?
Yeah, well, the first thing would be, well, the only thing would be that compressive sensing is in principle non-adaptive, in the sense that you measure in a way that will be general for any kind of signal. So you unplug the measurement process, the sensing process, from the nature of the signal, if you can. So you saw that some of the projectors there were simply random projectors, were matrices that were generated from Hadamard binary matrix with randomized columns. So the way you generate the matrices, or the most typical compressive sensing matrix, is a Gaussian random matrix. So a matrix where each of the elements is a Gaussian realization. In that sense, if you talk about independent component analysis, it would be a kind of optimal sensing matrix for a certain dataset. This you can say, but in principle it will be bounded, so you get the same chicken and egg problem. So if you tailor your system to a certain data, when you get a data point that was not expected because it was not contained, or better said, the nature of this data point was not contained in the dataset, then you will run into a problem. And compressive sensing tells you, if you measure in a non-adaptive manner, but you measure like we tell, so in this incoherent way, you will not be doing any worse than in an adaptive framework, in an adaptive measurement scheme. This is the difference. So compressive sensing in its origins is fully non-adaptive. So it senses completely independently from the data.
I think exactly this is the key point. ICA, I mean, the results that you got from ICA depends on the data set. So
Sure.
you change the data set and you change the components. So and here the idea is to have like an independent basis that can explain your data,
Yeah.
but independent of the specific data you're working with. So yeah, this is one of the points. But in terms of similarity, I mean, in both techniques, I mean, relies on the concept of sparsity, right? On looking for sparsity distribution on the signal, right?
Yes, but when you talked about independent components analysis, I would say you were thinking about generating the sensing matrix from the data, right? So in that sense, well, you already get the difference straight away. I mean, one could do, for example, a principal component analysis for the dictionary, or some other dictionary training method in general for the dictionary generation, and then mount a sensing scheme on top. And for this sensing scheme, you could have used a method that is designed with a certain dataset, or you could be completely non-adaptive and use these Gaussian matrices or pseudo-random matrices. So they are like two main blocks, right? So on the one hand, the signal modeling, so how you really get a sparse signal if you didn't have it, and later how you measure. So how you generate the sensing kernels to measure that signal. So these are these two matrices, which the product of which is this A measurement matrix that we put there before.
Okay, thank you for to clarify this, but I think it goes also in my line of thinking too, when I was thinking on comparing both techniques. The second thing is about the restoration problem. Probably, I mean, you know about all these Bayesian methods in which you have priors to make the sort of work. I think that Dobichet, the woman that has described all these bases, and well, she's one of the important persons, the field of compression, right? So she's working recently, in working with Bayesian methods for reconstruction, for recovery signals. I mean, have you made any comparison with Bayesian methods?
So, well, in principle, one can combine compressive sensing with a Bayesian method. This is true. This is something that we did not go inside. I would say no. We did not really work on that. Not the way you asked.
Okay, yeah, because I think you mentioned that if you have knowledge and you can build some priors, right, you could have additional information for recovering information.
That's true. And again, you have the same problem as usually, right? So up to which extent do you want to rely on previous knowledge? This is always like this. So for example, I was working before in robotics, and for the let's say the master thesis project, what was called the Proyecto Fin de Carrera in those times, was about a localization system. So our mobile robotics localization system based on RGB-D. So using a Kinect sensor, and it was pure localization, and it was not using any Kalman filtering approach, any IMU integration, and so on. So if you wanted, in that case or in this case, you can always implement the same within a Bayesian framework. In principle, it is possible, but then you have to really model those priors and be confident on that. So if you work in a video application, then I would say this is the way to go, and even modeling the sparsity evolution. So saying, okay, now we have this sparsity here, this combination of non-zero coefficients. In the next frame, the possibilities are this. So the sparsity, this sparse coefficient has moved to this other coefficient with this probability, to this other with this other probability, and so on and so forth. Yes, you can do that. But then again, it's application dependent, so to say. We did not really explore that option, but I understand that if you work in video, it would be probably very useful, because then all you have to recover somehow is the degree of innovation from one frame to another, and no longer the full information.
Yes, the degree of change, that's true. And the last question, you work with two channels. You have channel A and channel B, and I mean, it seems to be that these are some complement channels, right? That the information that comes by both these channels are, complement each other.
The integration is mutually exclusive. So when you integrate in A, theoretically, you don't integrate in B. So it's just that.
So my question is, how this AB channel, I mean, what was the idea behind this AB channel, of having these two channels?
We need the difference between them. So
why? The question is why. I mean, what was the reason to make this design?
Oh, well, that's a very interesting question, because in the beginning of the beginnings, I think the idea was to use one single channel and throw the rest. And I think some PMD pixel was, well, PMD, pre-PMD pixel was done with one integration channel, and when it was not integrating, it was throwing it away. and there is also another pixel with 4 integration channels. Problems are, if you have many channels, you can do only one single acquisition. You would not need these 4 sequential acquisitions. You could get your depth image with what you get from one shot, so to say, because you will get these 4 raw images in one shot. If you have one channel, then you need more acquisitions. So you will need, for each of the phases, 2 acquisitions. One measuring the whole intensity, and the other one with modulation. So with modulation at the control signal of the pixel. So because you need the subtraction, you need to remove the common mode. You need to remove the background light, and therefore you will be winning in simplicity of the pixel. You will
so the point is that you have 2 alternatives. You could have one channel,
yes.
So make the differentiation in time, or you can have 2 channels and make the differentiation in terms of spatial, right? Because you have the information at the same time, right?
Totally right. Yeah.
That's interesting.
Yeah, that's totally true. Problem is that the more channels you have, the more complex the pixel will get. The more problems you will get within the pixel, the worse fill factor you will have, and it's already bad, and so on and so forth. And therefore, that was the only reason to think about a one-channel pixel, because of the fill factor, because of getting smaller pixels and less blind areas, things like that. But it turned out, after really a lot of work, that the best alternative is a 2-channel pixel.
Very interesting. Thank you very much.
Okay, if nobody wants to say anything else, let's thanks Miguel again, and that's all.
Thank you.